Okay, perfect. Hello, everyone. I'm Ryan. I'm a PhD student in material science at Carnegie Mellon and a stream owner for machine learning applied to materials at ACE. Today, we have a very cool presentation, which active learning is used to design, print, test, and improve 3D printed parts in a completely autonomous fashion and with a very small number of experiments. Uh, Today, I'm joined by Professor Keith Brown, an assistant professor for mechanical engineering, material science, and physics at Boston University. Keith's research focuses on increasing the throughput of materials research, and he has made many contributions to this area, including receiving several awards from TMS and other organizations. So thank you very much for joining me, Keith. I'm looking forward to this presentation. We're going to hear about the research and then have time for questions after the presentation is finished. So if you have any questions, please feel free to enter them into the chat on the YouTube feed, and we will get to them for the presentation. So with that, I will turn it over to Keith. Thanks again for joining us. I really appreciate it.
All right, thank you very much, Ryan, and thanks to the folks at Aggregate Intellect for putting this series together. It's wonderful to be here. Thank you for all joining us out there. It's my pleasure to tell you about some of our work that my group's been doing, looking at, as Ryan mentioned, autonomous experimentation and additive manufacturing. And to jump in, I want to highlight that there's a really consistent problem people see in material science and design, and that is the culmination of three major challenges. The first challenge that we experience is that we can have parameter spaces that are enormously vast. So we have many possible knobs we can turn, many choices we can make. And then ultimately, a lot of experiments are going to be slow or expensive. And so these are ones that require manual labor, they require equipment that's large and slow to use and expensive. And then finally, the final sort of piece to this challenging puzzle is that you can have computation that itself cannot perfectly capture experiments. So you cannot, maybe it's not fast enough, or the required precision makes it very slow, or perhaps it's just simply we don't have the technology needed to capture the property of interest with computation. And to show you why these three pieces are critical to as a major challenge, let's think about what happens if any one of them wasn't a problem. For example, if computation was fine, was an acceptable solution, then you could just compute and explore the vast parameter space and not have to do the experiments. If, on the other hand, if experiments were cheap, you could just use high throughput experimentation and just do lots and lots of experiments. Now, if your parameter space isn't big, then I think the answer is quite simple. You can just do experiments manually, do it very slowly. This ultimately, I think, is where a lot of PhDs end up, is that you end up having PhDs worth of research is a list of experiments you do to sort of in this space where experiments are slow and they need to be done. So the question we want to answer today and to talk about is really this question of, what about this middle area? What about where you have all three of these problems simultaneously? What can you do? And one technology that has come to really the light in the last couple of years, but as you'll see is more than a decade old, is that of autonomous experimentation. Now, this is a really interesting branch of research that combines two key elements. One element is the idea of automation. Now, this is if you have robots doing experiments, these experiments can be done more quickly and more reliably than people can do them. And the second branch is active learning. Now, active learning is a really interesting kind of subfield of machine learning. It actually dates back to the mid-90s, where the idea was if you use a machine learning algorithm to choose its own training data, rather than you choosing the data for it, you can actually vastly accelerate the training process. And actually, some of these early works show that you can take problems that were not polynomial and make them converge in polynomial time, which is important because it means that as the problems get bigger, this actually gets more effective. And so these two ideas existed and been used very robustly. And so the question is, what happens if you put these two ideas together? Well, then you can comprise something that is what we would describe as an autonomous researcher, where you have a robot that is doing experiments manually by itself, and then choosing them to sort of best converge towards an experimental goal. Now, this idea really is credited to Ross King and collaborators, who published the first paper back in the mid-2000s, and they developed the system they called Atom, which is basically was this large robotic system that allowed it to study yeast genomics and understand how metabolism of yeast works. And you can see that it's comprised with a lot of disparate pieces that sort of stitch things together. And a lot of what they leveraged in this system was the idea that you can have off-the-shelf robotics from the biological apparatus, things like the Human Genome Project that had found ways to vastly parallelize this. But a lot of these ideas can't necessarily translate easily to material science or to mechanics, where we don't have standard form factors for these kinds of experiments. And so it's actually been the adoption of this idea, this autonomous experimentation idea, in other fields has been comparatively slow. In fact, the next major breakthrough came in about 2016, where Benji Maruyama and colleagues at the Air Force Research Laboratory figured out how to synthesize carbon nanotubes using a simple, scalable robotic system that they described as Ares. And so this system where they have basically a small scale reactors that they can actuate with a laser and read out with a laser, allow them to measure the growth rate and to have a feedback process that happened very robustly at the small scale. And so this allowed them to make what is understood to be the first autonomous experimentation system in material science, which really is kind of striking. This came more than a decade after it sort of made its breakthrough in biology. And so in the past couple of years, this idea of autonomous experimentation has actually taken off quite a bit. There's been a lot of papers that came out even as recently as last year. There's been some great work, for example, out of Canada, looking at how we can make interesting thin films or organic materials for optimizing its optoelectronic properties. There's some work out of the UK looking at how we can optimize catalysts, all using robots, in this case, that sort of move by themselves around labs. And so there's been a lot of great work coming out, and I hope you check out some of these papers that are listed here to read about some of that. And so what I'd like to tell you about today are some of our work answering some kind of fundamental questions in this field. Now, we got interested in this because we were studying robotic systems and trying to accelerate research, but we realized pretty early on that there's actually a few major open questions in this field. The first question that is one that we can address to some extent, but really needs to be answered in order to justify this work altogether, is to understand, how much can this actually speed up research? I mean, we can say that obviously it's good to have automation, obviously it's good to have active learning, but until we can benchmark that against an actual experimental campaign in an experimental system, we don't know how much this actually accelerates research. And the second question is a really interesting one from the perspective of, as researchers, because researchers tend to be hypothesis driven. We make a guess about the world, and then we try to explore that guess. Now, a lot of machine learning is data driven, where you basically look for trends in data, and that guides the next experiment. And so is there a middle ground? Can we find a way for these autonomous systems to basically function as hypothesis driven systems? And so these are two questions we wanted to study when we got into this area. And the kind of area we are looking at here are mechanical properties. And so I want to take a second to talk about mechanics and the kinds of properties that are hard to optimize. And that is, so if you're familiar with stress strain or force displacement curves, you'll know that, initially when you push on a material, it'll push back like a linear elastic spring. This is the elastic limit here in this stress strain curve. And then at some point, it's going to start to yield. And this is when the material starts to break, the bonds start to break, and then you have this post-yield behavior, and ultimately material fails. Now, this is a really interesting regime. So we know pretty well how to predict elastic mechanics. We might even know in most cases how to predict yield. But once you get past yield, post-yield behavior of materials is very difficult to predict. But it's also very important. Take, for example, the idea of a crumple zone in a car. The crumple zone in a car is designed such that when a car gets in a car accident, that will deform plastically. So you're in this regime here, this plastic regime, and therefore you're doing work on the car. You're actually breaking bonds and bending metal, et cetera. And that is dissipating the energy to keep the passengers safe. And so this is an important thing to optimize from a safety perspective. Unfortunately, it's extremely difficult to model. And so this really has all the criteria that I laid out before of a challenging problem that we need to think about that autonomous experimentation could help with. That is to say, there's huge amount of possible parameters we can choose. We can't perfectly compute this in advance because there's a lot of things like self context and geometric and material nonlinearities that are very difficult to model. And then, of course, experiments are slow. Imagine having to crash a car every time you wanted to change any minute detail. This is what you're talking about. So this is a challenging problem to address. So we're going to employ autonomous experimentation to address this. And so let's start. So I want to start by talking about how we dove into this. Now, the first question is that of automation. We have to find a way to do these tests in an automated fashion, that is to say, with no human intervention. And the first technology we want to leverage to do this is one that is going to enable us to have tremendous geometric flexibility. and that is the technology of additive manufacturing. And so this is an idea that has really taken off in the last couple of decades, which is the idea that if you use a system to additively build materials from the layer by layer fashion from the ground up, rather than using a subtractive process to put together nuts and bolts separately, you can dramatically improve properties. And so this is a great example. If you're not familiar with this one, I encourage you to read about it. It's wonderful. It's an example of how you can basically take this is one of the earlier examples of an additive manufacturing we use in an aerospace application. This is a fuel injection nozzle that's been printed monolithically, so it's one part. And this is replacing something that would traditionally be about 20 parts. And it does this by being lighter and cheaper, in addition to, of course, making the supply chain tremendously simpler. And this is actually used in this particular LEAP engine, which is used, which has been developed by GE in collaboration with this LEAP company. And so the question is, okay, so additive manufacturing is already a tremendous capability that allows us to realize components. So it allows us to do something like take a digital design, for example, an STL file, turn that into a physical object. Like this case is a printed part. We're going to be talking mostly today about fused filament fabrication and printing polymer components. But then you can take that component, at least in principle, and then you can do an experiment to measure a force displacement curve, for example, here to measure that post-yield behavior in a real space. Now, the challenge here, though, is that this is not especially fast, right? So making a polymer component might take, hours or so. Making a metal component might take up to days. And then the testing process has to be done in a serial nature, which typically involves a lot of human intervention. And so a couple of years back in about 2016, we had the idea of trying to do this process, the whole fabricating and testing process automatically. And so we actually pitched this to a senior design team at Boston University. And what they came up with is what's shown on this slide, which they described as the Auto Crusher. It's a system that combines a 3D printer, a mechanical arm, and a basically home-built universal testing system that allowed them to sort of print a system or print an object and compress it to failure. And they designed this as part of the senior capstone project. This is the team listed down here. They did a wonderful job. They actually won best in the show that year, and they realized the structure. It's really remarkable to think about the really small budget, about $400 plus a little we kicked in, but basically allowed them to realize this really fascinating structure. And it did function at least a few times. And so they showed that it's possible. If you construct a system carefully and position the automation just so, you can realize this idea. And so we took this idea and ran with it, and we realized a system that was a bit more involved. And this is the system that we built that is the one that's sort of operating today. And it's combining 5 printers that are each dual extrusion, that they're in the working radius of a 6-axis robotic arm, as you can see here. And then once parts are completed, they're automatically retrieved. They're weighed on a scale. It turns out that actually that quality control is being very important, as we'll see in a second. And then they're tested to failure here using this Instron testing system. And so this allows us to test and to print and test about 60 to 90 parts per day, depending on the kind of part we're talking about. And it's all done without any human intervention. This video is shot over about 8 hours. It's been accelerated to highlight. Of course, those of you who've watched 3D printing know that it's kind of boring to watch in the slow scale. But so what does this allow us to do? Well, it allows us to take this idea of printing and testing, but rather than thinking about, okay, I want to test one component, measure one force displacement curve, we can do this in a larger scale. For example, we could study 240 of the same part. Why would you want to do that? Well, here is the sort of forest of curves produced by these kinds of parts. And you can see there's a lot of variation. And this is one thing that's been a notable kind of difficulty with additive manufacturing is the parts have variable quality. And so this allowed us to say, well, how much does that quality vary? And can we understand that? And so here's, for example, the toughness of those components versus their mass. And so you can see that there's a pretty reasonable variation in mass, about a 5% coefficient of variation here, but a much larger variation in the toughness of the components, toughness being the energy that's dissipated when they catastrophically fail. And one thing that's really notable, though, you can see here is that there's a correlation. So parts that are heavier tend to be more tough, and parts that are lighter are less tough. And that actually allows us to say we can non-destructively measure the parts, we can weigh them, and we can actually capture about half of the variance of their toughness with that. So that provides an important window, and is the kind of result you might only get by having this kind of large scale, high throughput experiment. And so in addition to allowing us to sort of measure lots of samples of the same kind to capture things like variance, this also allows us to do more interesting things from a design perspective, because now instead of thinking about individual parts, we can think about families of designs. And so to explore that idea, we designed something we called the cross-barrel family of structures. And these are structures, and there's about 500,000 distinct of these structures, but they're composed of 4 different parameters. So we take basically a column a hollow column of thickness t and radius r. We put n of them in a circle, and we twist them with some angle theta, and they give us these kinds of structures of this characteristic. And the thing about these that are really interesting from a mechanics perspective is they have a tremendous variety of mechanical properties. For example, they can be reasonably brittle. And so these are ones that once they experience a yielding point, there's no structural resiliency after this. They fall apart completely, and you can see they just shatter. So these would be a brittle structure. You can also have structures that are quite ductile. And so these, after yield, they maintain some of their strength. And so they actually, if you look at the area under this curve, shows that their toughness is quite high. So these would be high-performing structures from a toughness perspective. And you can also have structures that are too strong. And so how could you have a structure that's too strong? Well, think about that example of a crumple zone, right? In a crumple zone in a car, if the crumple zone is so strong that it doesn't crumple before other parts of the car crumple, for example, the passenger cab, then it isn't fulfilling its design criteria. And so anytime you're designing for toughness, it's important to say a maximum strength that you have to specify before the structure starts to fail. And so here we can define that to be about 5 kilonewtons. And so these will be, therefore, a low-performing structure from the perspective of toughness. So we have this parameter space, and so the question is, can we explore it using this automated system? And so the way we think about that, we can try to define that space for you. Unfortunately, it's a 4-dimensional space. We can't visualize it in one axis, but what we can do is recognize that, so of these 4 variables, 2 of them are discrete. For example, we have a discrete number of columns. We have a discrete number of lines of the thickness of the columns. And so here's the number of columns sort of increasing as you go down, and then the thickness is increasing as you go to the right. And each of these squares, these rectangles rather, correspond to the 2 continuous variables, the radius of the columns going up on this axis and the twist angle theta going up along this axis. And so here we have this is the depiction then of this 4-dimensional parameter space, and we can define a series of locations. And so these dots correspond to the locations, and each of these locations we can test the sample. We can test this parameter space there. As we do this, there's 600 locations. We test each in triplicate. So we perform 1,800 experiments using this automated system. And so in doing that, we can then create basically a map of performance as a function of location in this parameter space. And so you can see that, so here you have this the toughness of this based upon this grid benchmarking measurement. And you can see there are regions of low toughness, regions of high toughness. And we can say, well, where's the best part? Well, we think it's right there based upon these measurements. Okay, so this automated system allowed us to do what is basically the classic way of doing experiments, where we do lots and lots of experiments to exhaustively explore space to identify what we think is the best component. Now the question is, can we do better? And can we do better by incorporating this idea of active learning? Can we actually realize an autonomous researcher? And spoiler alert, yes, we can. And so to understand exactly how that can work, I want to go into a bit more depth about what active learning is and how we can visualize that. And so let's just take a step back and say, well, when we talk about doing research, we talk about doing an optimization, what are we actually doing? Well, so in reality, there's some function we want to understand. And so we can call this the true function. If you're into machine learning, you'll probably call this ground truth. It's a response function. It's the function of some number of parameters. We'll just start by calling it one parameter x. And the idea is that we can vary x, and we want to understand, maybe maximize this function with respect to x. And all we can do, though, is we can do experiments or observations. We choose a value of x, we measure that. And so here we would have some dots on this curve. This is even assuming that there's no noise associated with this. And so the way we would study this in sort of a conventional standpoint is we would perform an experiment, we would collate that knowledge in our head, and we'd choose the next experiment, and we'd repeat this process until we were satisfied. And so the strategy I want to talk about basically systematizes this using an algorithmic perspective, and that is known as Bayesian research campaign. The idea of a Bayesian research campaign is we're still performing experiments, but now these experiments are then collated with prior knowledge with these experimental results to form what's called a surrogate model. Now, the surrogate model represents our belief about the true function given the knowledge we have, that is to say, any prior knowledge and the experiments we've done so far. And what that looks like is what's shown in green on this curve, where we have this green line that corresponds to the mean or the expectation of that belief. But then we also have the shaded region, which corresponds to our uncertainty. And so you can see where we've taken measurements, uncertainty is low. We think we know the function pretty well there. When we haven't taken measurements, then the uncertainty is high. And so this provides 2 important advances. This means that we can say, okay, at any given time, we can say, where do I think the maximum is? And so here, maybe I think the maximum is at this point, which you can see is actually quite a bad guess based upon what the actual function looks like. But the other thing it allows us to do, which is really fascinating, is to employ what's called the decision-making policy. We can basically take the surrogate model and put it into this decision-making policy to find a way to choose our next experiment to give us a maximum advantage. And so there's a lot of different decision-making policies we could discuss. I'll discuss one that I think is quite valuable from the perspective of optimization, and that is what's called the expected improvement decision-making policy. Here, the idea is you look at each point of your surrogate model and you say, now what is the likelihood if I sample at this location that I'm going to find an improvement in my belief of the maximum of the function? And so here you can see that, areas where we have already sampled, these expected improvements quite low because we think nothing is going to change if we sample there. But regions where both the samples, our belief is reasonably high and there's a lot of uncertainty, this is a good place to sample because it means that we think that there's a good chance we're going to improve the situation here. So in this case, you can see the expected improvement is peaked at this location. You might say the acquisition function is peaked at this location, which means we're going to sample here. So now what you do in an active learning loop in an autonomous system is say, okay, so sample there. And so you perform a measurement there. You can see that measurement was quite bad. And so you dutifully update your surrogate model. And then you say, okay, well, now the next place I can sample is over here. And so you sample there and time goes on. And so a couple things you should note about this. So of course, the samples you're measuring haven't been good. They've actually been quite bad. But even so, even though the samples have been bad, your belief is actually more closely matching the real function, the true function. And as a result, you're actually learning, even though you're not measuring samples that are good. And in fact, as time goes on, as you start to sample, for example, then things that sort of more closely match the maximum, you can see that you've not only found the maximum, but you've also learned the whole function. And so this is a really interesting facet of this, which is that when you do a campaign based upon this kind of Bayesian campaign, you're both simultaneously learning the space and also finding the maximum, which is really tremendous. And so, can we do this in practice? Well, this is a challenging thing to do, as you might imagine. So I've already told you how we've built a robot to basically test, print samples, manipulate them using a robotic arm, and then compress them to failure. So now what we need to do is we need to combine this with belief modeling, where we sort of build our belief about the model of the system, choose the next experiment, and then design it, and then print it. And so in this part, I just want to put my hats off to the students that made this all possible, Derek Gongara and the rest of the team, because they basically found a way to use MATLAB as a kind of central core, and then to control basically a dozen other different kinds of software to basically make this all happen without computer interaction. So components are designed, manipulated, printed, tested, interpreted. All of these things happen, including the machine learning, all without any human interaction. So this really then becomes an autonomous experimenter. And so let's test out some campaigns based on this. And so I'll just mention, by the way, that because of we were very interested in finding a shorthand to call the system, so we decided to call it the Bayesian Experimental Autonomous Researcher, or the BEAR. And so this is what a campaign run by the BEAR would look like, again, an experimental campaign. And so I'm going to show you two. One is governed by what's called a maximum variance decision-making policy. So this is a policy that really focuses on exploration. So it's going to say, wherever I know the least about the function, I'm going to sample there. And so starting at this point, it's going to explore space. And so I just want to remind you that this is the location in space that corresponds to what we think is the best from this grid-based study. And so I'll start a movie now, and so you can see the points are starting to fill in the order they're tested, and you can see they're spread out. Basically, the function is basically choosing points that look more or less completely spread out in space because it's only sampling where it doesn't know very much. And so in this case, after the experiment concludes, it might say that the best it predicts the best result is over here, which actually, interestingly, is not a region it's even sampled. Now, if we compare that to an expected improvement policy, again, we're going to start randomly at this location. And now, once I start the movie, points will start to appear in the order in which they were taken experimentally. And so you can see that in contrast with maximum variance, they're really clustered around where they know information, and they start to find things that are high performing and then really spend a lot of time there. And then eventually, but you can see that they're really balancing this idea of exploration and exploitation, spending a lot of time exploiting these high performing regions, but also capturing regions where it knows very little. And in this case, this policy believes that you have the maximum of performance here. And so this raises an interesting question, though, right? Because these orange shapes correspond to what we think the best is from this grid-based 1,800 experiments, and these other 100 experiment campaigns found different locations. So the question is, who's right, right? And we can go further and say, well, if this is the whole space that's found by this grid, and these are the result of 3 different campaigns that ran 100 experiments each using this expected improvement, and we can also look at 3 campaigns that use this maximum variance. And they all came up with different locations, and none of them came up with the location found by the grid. So the question is, who's right? Now, this is in our group, we have a saying that experiment is ground truth, because ultimately, we're talking about physical systems. And so if we want to understand who's right, we have no choice but to do experiments. And so what we did is for each of these 7 locations, we printed 10 samples and we measured their performance. And so here is an example. We have 10 samples looking at the toughness of those samples. And so you can see that the grid-based sample, which again used 1,800 experiments, came up with about 35 joules. And now 2 out of the 3 maximum variance campaigns, which again are not designed to exploitatively find these maxima, they're just exploring. 2 of these 3 beat this in the 100 experiments they had allotted. And actually all 3 of the EI campaigns were able to not just match, but outperform this 1,800 experiment. And so showing you that in this case, 1,800 experiments are not as good as 100 experiments that have been well chosen. And we actually went further to say that, can we do better than this? Because, what would it take to just match this performance, for example? And one of the things we were interested in is not just number of experiments, but also speed. And so we performed a kind of a second type of experiment where we said, well, now what about if instead of having each of these sort of printers acting independently and running separate campaigns, what if we just ask how quickly, using all of the resources at our disposal, how quickly can we design a good component? And so in this, we have all these working together, and we found is that after merely 12 hours of studying, we'd actually already studied 32 samples, and we'd already matched the performance of that 1,800 experiments. So in just half a day, we're able to perform 30 experiments that basically were about 60 times faster in terms of number of experiments, but more than that times faster in terms of time, because the campaign to take all 1,800 experiments took several months. And so this is really a tremendous acceleration. And as time went on, we found better components that started to outperform what we found in just the 12 hours. And so showing you again that, the value of choosing the right experiments and how this autonomous system gives you that for free, because it will automatically take into account all the prior knowledge in choosing every subsequent experiment. And so I've talked about optimizing a structure, so I have to show you the optimized structure. And so this is an example of what we found to be at this stage anyway, the toughest of these cross barrels. And you can see that you have this really intricate series of yielding and bending and the sort of densification regimes. It'd be really difficult to imagine designing these in a sort of rational fashion so that it would work constructively. And so this is showing this is what you get out of this sort of optimization process. And so this is, where things stood about a year ago. And then, we asked the question, well, okay, so this process, we really treated this like a black box. So where we had some function we wanted to optimize, and I told you it was a 4-parameter function. And we did experiments to optimize it, but this could have equally worked as well for any other property, whether it's, it's something from nanoscience or biology or whatever. But we know more than this. Like we know more than we let the system go and know. So the question is, can we improve this? In particular, can we put knowledge into this somehow that further accelerates the process? And for this, we want to take an idea called transfer learning, which is basically another idea from machine learning, which says, if I have a related problem, can I take information about that problem and put it into my system to make things converge faster? And the related problem we want to talk about here is that of simulation. It's because simulation is a way to robustly and rapidly find some information about the system. And for those of you who are interested in simulation, you probably well know that this has been a tremendously useful tool in, for example, the area of topology optimization, where, for example, you can choose the shape or iteratively improve the shape of materials to best match manufacturing goals, and using based upon simulation to robustly find properties that can easily be simulated. And so our first task was, okay, can we do this? Can we take these 3D printed parts and rapidly simulate them? And so the first task was we'll just design a way to do that, right? How to take this 3D printing file and just simulate it, which actually ends up being pretty non-trivial. Because when you think about a 3D printing file, you have this STL file, which is not actually a great CAD file. It has a lot of properties that don't make it ideal. So the first step was to, for example, build a voxelized representation and then turn that into a mesh for simulation. So then we can simulate this. And we're going to use Abacus to do this. And so here's an example of a simulated response. We can get this force displacement curve up to about the yield point. And so if we compare that to the experimental response with the same geometry structure, you can see we're basically capturing just this initial little triangle here, this elastic response. And that kind of agrees with our broader understanding, at least of our simulation capabilities, that measuring this whole curve, this whole toughness curve, would be very challenging. But we can very accurately measure just this little triangular region, which has an important property, and that's called the resilience in the mechanics community, because that is the property that defines how much energy can be absorbed and then given back elastically. So this is something that if you have a spring resilience is what you care about because you want to know how much energy you can absorb and give back. And so we actually can study that. And so we said, oh, well, can we match that experimentally? And so, for example, if you look at a cut through this space, and we look at the resilience both from simulation, which is shown in green, and experiment shown in blue, you can see that both qualitatively in terms of the shapes of these curves, and also quantitatively in terms of their magnitudes, they're a pretty good fit. And you see the same kind of characteristic behavior here. And we can look across the whole parameter space, and we see that in terms of the simulated versus experimental resilience, there's good agreement with a sort of 0.1 joule kind of root mean square error. And so we can predict resilience. And so can we use this to help us learn? And so for this, we're going to borrow an idea from transfer learning called relational knowledge transfer, which is the idea that we can take related knowledge and add into our system. And so to do this, we're going to basically say, all right, we're going to assume that FEA is right. And we're going to, instead of learning the resilience of the system, we're going to learn the difference between the resilience that we get experimentally and the resilience from simulation. And this is called the discrepancy model. And it allows us to basically use this FEA modeling as a baseline. And so what we found in doing this, and so we compared 3 cases here. So we have the FEA-informed bear. So that is the bear that we are using the FEA as the starting point. When we have a bear without FEA, so this is just what we've done before, which we call black box optimizer, and we're also comparing it to this grid-based experiment with 1,800 experiments. And so here's resilience as a function of number of experiments. These are the actual samples we collected. And what you can see is that immediately upon starting, basically after the first experiment, the FEA informed bear immediately outperforms the grid-based study, like right away. Whereas the bear that without FEA, it does get there, but it takes about 30 experiments. So we can address this a bit more rigorously by looking at sort of at given time points in experiments after 3, 10, or 30 experiments, we can find what we believe is the best component in that model, and we can measure their resilience. And we find that even after 3 experiments, we've outperformed this grid, which shows that if you have good prior knowledge, even 3 experiments can beat 1,800. So, a factor of 600 types of improvement, which is really tremendous. And so this is, really communicates clearly that if you have a good prior, you should use it, and that's going to dramatically accelerate the process. And you can still get new information by measuring this discrepancy to figure out where your simulation is not capturing the physical behavior. And so then now the more interesting question, though, is, well, what if you don't have a good simulation? What if you don't have a good prior? And so if we look at, for example, the toughness, so here we have resilience again, this little triangle region. So toughness is this whole area. So the question is, what do we do there? And so here is, for example, looking at the simulated resilience versus the experimental toughness, and there's no correlation. You can see that these points are randomly distributed. We have no ability to predict this. So the question is, what do we do? And this ended up being one of probably the most intellectually stimulating parts of the project, because this really comes down to one of the deeper questions of learning and how we build knowledge as people, which is, what if we have related knowledge, but it's not the knowledge we're after? How do we use that? And that really forced us to be creative. And so we thought about this, and we recognized kind of that there may be multiple paths to incorporating this. And so one thing we said is, well, based upon our knowledge of the mechanics, maybe we can find other ways to include this data. And so one observation was, okay, well, we acknowledged earlier that there's a strength limit, right? If materials don't yield until until a certain stress, then they're too strong for our toughness application. Now, in that case, we can predict the yield force from simulation. That's one of the things we can predict. So perhaps we can just use that as a gate and say, if we look at a given component, if it's predicted to be too strong, we're not going to look at it. We're going to exclude that from the consideration, because we're going to say that's going to be too strong. It's going to be low performing. So we can basically use this process to filter parameter space to remove structures we believe are too strong. Now, another idea we tried to sort of bring simulation knowledge into the experiment was one that I think is really shows the power of this approach as a way to generate hypotheses. And that is this idea of thinking about toughness at a bit higher level. Now, toughness is, I would say, the canonically difficult material property to optimize, because it requires that 2 things that are typically at odds are both true. So typically, materials are either strong and brittle, or they're weak and ductile. And toughness requires that they're both. So materials are both strong and ductile. And so we said, okay, well, is it possible to separate these 2? Can we, for example, can we acknowledge that, can we look at strength from simulation, and can we look at ductility as a measure of the toughness measured from experiment? And so if we conceptually separate these things, perhaps we can learn them more effectively. And so to do that, we said, okay, so rather than sort of measuring this toughness from experiment and just using that as the toughness is the thing we're trying to learn, what if we take that toughness and then divide it by this force that we get from from this simulation. Well, that would give us a measure, imperfect, but a measure of the ductility of the structure. And so, what if we try to learn that instead? Then, the question is that could be more effective. And so the nice thing is we've actually, because we had studied this parameter space already, we can make a guess as to how much that could help things. And so we can basically compute the minimum number of experiments that we believe are required to understand this parameter space. And so we know that without FEA, just the black box system, it would take about 80 experiments to do this. Now, if we remove the experiments that are too strong, we find that really lowers it down by about 10% because we're removing about 10% of parameter space. However, if we seek to learn the ductility, it should only take something about 20 experiments to learn this parameter space. And this is because the correlation lengths are longer. When you take a measurement at a certain location, it will be relevant to things that are further apart because, again, these correlation lengths are longer. So this could provide a path to really dramatically accelerating this process. And so let's test it. And so we performed a series of experiments using FEA as part of the belief model, as part of the decision-making policy, and comparing it against what we called the naive bear, otherwise known as the bear without the finite element analysis. And what we saw was kind of interesting to us, which is that if we look at these two comparisons, and again, after 20 experiments, some of these campaigns found extremely good structures. In fact, even after 20 experiments, one of the FEA-informed bear campaigns found a structure that was better than any we had seen before. And that actually remained true after 60 experiments. But some of them were really, really poor, actually. And that's interesting because the reason they were so poor is because they were looking kind of right at this cusp where structures were too strong. So if they were just a little bit over optimistic, they got structures that were quite bad. But again, after about 60 experiments, most of them were above the sort of bar. And in fact, at this point, we found that we had about a 75% chance of improving over the naive bear, the bear with FEA, and then the average improvement was 15%, which is really noteworthy considering that the improvement we had of using the bear in the first place after 100 experiments was only about 10%. And so what this is showing us is that there is a way to sort of take this related knowledge and put it into this campaign and to take value from that. And not only that, but it can be used even if it's not a directly related quantity. And so where does that leave us? Well, so we're quite excited and proud about the idea that we sort of realized this bear to test mechanical structures and to combine the ideas of additive manufacturing, mechanical testing, machine learning. We are very excited to continue to work on this in the years going forward. And so the first question we pose is, by how much can this speed up research? And we've been very excited to report that we've done some great benchmarking here, looking at, for example, how looking at how the grid-based experiment, with 1800 experiments, how that compares against these autonomous experiments or physics-informed experiments, showing that we have in some cases factors of 60 or more acceleration in terms of numbers of experiments. We hope that these kinds of metrics can be useful to others to motivate their autonomous experimental systems, so we can find ways as a community to sort of push past the benchmarking idea and now to really get deeply into the discovery phase. And then there's a second piece, just to emphasize, we've been able to show that, you can take prior knowledge, and the way you incorporate that prior knowledge really can constitute a hypothesis for how your system is behaving. And we think that's a really powerful idea that can take this away from, sort of what people think of as a data-driven process to really a hypothesis-driven process. It makes the autonomous system basically an extension of your brain as an experimenter, where this is saying, hey, I have this idea I want to test, and instead of having to craft the experiments, think about what experiment I do next, I just give this idea to the system, and the system tests it. That really becomes quite a powerful and enabling idea. But ultimately, and thinking about where we're going next, we spent more than 3,000 experiments looking at how many it took to learn, and we found it only took 30. And so this means that in terms of parameter spaces to explore, problems to address, we need to be much more ambitious. And so that's what we're working on now, is sort of spreading out into much more complicated spaces, much more intricate properties. And so I'll conclude by acknowledging the team that made this possible and the support we've had that enabled that. So the graduate students made this possible. I've primarily told you today about the PhD work of Aldera Gongora. It's also help from a number of other folks like Bo and Ju and Kelsey Snap. This work has been also a collaboration with Elise Morgan, Chris Reyes at University of Buffalo, Patrick Riley at Google, and a number of other folks. And has been supported pretty broadly, as you can see, but most notably by Google and the National Science Foundation. So yeah, thank you for your attention. Very happy to take any questions in the chat here.
Right. Thank you so much for that presentation. The fact that you were able to get 100x improvement in the number of experiments is like absolutely mind blowing to me. So it's just a very cool project. So I had a couple questions. I guess I'll start with just the experimental setup first. So when you print the parts, you usually have to like preheat the bed and control the temperature. It looked like the robot was just picking up the parts and putting them on the mechanical tester. Did you control for the temperature of the part on the compression test? Because I know sometimes the properties can be temperature dependent. So I'm wondering if that could have been a source of variation.
Oh, it's a great question. Yeah. So a few things to note. So when I guess the first thing, we did not measure the temperature of the parts, but we have reason to believe that they're basically room temperature. And the idea for that is that we actually needed to let them cool pretty far down before we could actually get them off the bed. If you're familiar with this kind of printing, you know that part adhesion on the bed, one of the reasons you heat the bed is because it makes them stick well. But that's also a problem when you want to remove them, especially automatically. One thing about the robot we use, it's a Universal Robotics cobot, is it actually has a force limit. So if you try to apply a force that's too large, it'll actually just stop automatically. And that's meant to be what's called a cobot work, within human environments. And so getting that to sort of automatically pick parts can be challenging. One thing we did with that is basically just let them cool down. That's the simplest thing to do, right? And actually, in the video I showed you, you can kind of see that because in the sped up video, after the parts are done, they're kind of sitting there for a few minutes. And so that we cool them down to basically room temperature. And by the time they get to to the testing system, we have reason to believe they're effectively at room temperature.
Okay, makes sense.
Yeah.
And then so also before measuring the compression performance and the toughness, it looks like you weighed all the parts. So I'm wondering if you found that designs that weighed more because the thickness of each of the cylinders was like kind of an easier factor to predict the toughness. Like I guess the different designs had different masses, right? So I'm wondering if there was
Yeah.
any
Yeah.
dependence on mass on toughness, because obviously if you have really thin cylinders, your part's probably not going to perform as well than one that's printed with twice as much material until you hit the limit where it's too tough and then undergoes brittle fracture.
Yeah, that's a wonderful question. I mean, the short answer is I don't have a plot in this presentation, but we did in our paper we did present a what you might call the gamut, like a plot that showed the toughness versus the mass of all the components. And there definitely is a correlation where tougher parts tend to be the heavier parts. But it's by no means it's by no means simple. It's more like kind of a large blob of parts that they're inside the parts that are heavier. They're those that are tough and those that are not tough. So I would say there's definitely more. I would say it's more likely for parts that are heavier to be tougher, but that's not the whole story. Yeah, that is a great question though.
Yeah, it makes sense because you start hitting the really nonlinear parts of the stress strain curve. So um,
Yeah.
you get very different results for similar designs.
Sure.
And then I'm also curious, you said your students were able to just string together everything in MATLAB. So like how much hacking was required? Like you have these off-the-shelf components. Do they have APIs that you can easily use to control them? Or did you have to do, or was it very difficult to actually get everything to play nicely with the computer?
Yeah, so I'll answer from my perspective as the person who didn't do the actual work in this case, but saw it all from the students wrestling with it. I mean, we tried to label in this case where all the different pieces of software we used, right? And so MATLAB did most of the heavy lifting in terms of the processing. There were some things that were pretty difficult to do. I think managing the so I'll give you two examples of things that were a little bit tricky. One is that we really wanted the computer running the Instron to not be the same computer as the one running the rest of the learning loop. And that's because one of the sort of manufacturer specs of the Instron computer is that it has to be doing nothing but running this Blue Hill software. And that's, I believe, because there's important for it to have real-time communication and not have interrupts or something like this. And so for that, we had to manage data back and forth, and and getting that seamlessly was a little bit challenging. That the other piece was actually controlling the instron and getting it to start, because there are software ways to do that in an API, but it's extremely cumbersome. So actually, this is an example where the way we ran this is actually a way to use like digital logic to run the system. So it's actually just like you can have a wire, and when that wire goes to 5 volts, it starts the next test. And so there in between MATLAB and the Blue Hill software is an Arduino that was turning on a voltage to 5 volts. And so, then these things would sort of, there were a few examples like that of things that were happening that might not be, if you were able to make all this from scratch, it's probably not how you would do it.
Yeah, I love it though, using the Arduino to just will the system to work.
Exactly. Yeah.
That's probably going to be a consideration for equipment manufacturers in the future, is as these automated approaches become more and more common, they're going to want to start actually developing open APIs that people can do this more easily. Um, so don't remember if you mentioned what material you're using, but I'm guessing all of the experiments were conducted with the exact same material, like that wasn't part of the design space. Do you think you could use categorical variables, such as using different types of materials as part of the active learning process? So I know some methods require like there to be gradients or
Right.
the magnitude of the value to be relevant, but with categorical variables, that's not always the case. So do you think that's a way or a approach that could work with this, or would you just have to run separate campaigns with different materials?
Yeah, that's a really good question. So, and actually dovetails nicely into what we're doing now. But yeah, to answer the question that you assumed that we were using the same material, and we were using polylactic acid, which for connoisseurs of this kind of printing know is sort of the that's like the white bread of material, right? It's like the simplest thing that works easily, and it's very very effective. And it's not as not as maybe tough and high performance or strong as like ABS or something like that, but in terms of printability, it's very robust. And that was one of the things we were prioritizing in this initial study, is we wanted to work most every time, so we could do things like run it over the weekend and not be there, which are things we did. So going forward, we are indeed we've branched out to other materials. And actually, one thing that's really interesting, I'll just move to just show you kind of the picture of the, like right now, as we have a bunch of different printers, we actually currently are running campaigns where we have different materials in each printer, and actually more variables different than that. And so your question of how do you incorporate them to a learning loop is a really an astute one, and kind of buried within that is, what is your surrogate model, right? Because your surrogate model, in our case, I didn't really describe this in depth, and your community might really be interested to know that we are using primarily Gaussian process regressions as a way to build interpolations between space, which of course requires that this is there's a numerical value you can compute. And so the question of how to, if you have categorical data like different materials, how to do that is tricky. And I'll say that there's the way that we're approaching this now is to not have the material be stored as like PLA, but stored as a material property, right? So say store it as its stiffness and density and toughness, or its yield strength or something like that, right? So you have so materials are defined in using variables that you think are important as a way of sort of getting around this idea of having just a simple categorization.
Okay, that makes sense. Then, so I guess most of the questions I've been asking so far have been materials related. I'll try and branch more to the machine learning side of things. So for selecting the proposed designs, like how does the system choose its first design? Like, do you give it some prior knowledge by running like a small number of experiments and saying like, for this very wide grid search, we know these properties, or do you just let it guess at random?
Yeah, so in every campaign we did, the first experiment was selected uniformly at random. So so there were campaigns where we had physics knowledge starting with, we used FEA to sort of give it prior knowledge. But even in those campaigns, the first experiment we did was always you selected uniformly at random. And that the phrase uniformly at random, thanks to Chris Reyes for making sure I get the terminology right there.
Yeah, because I guess that could be one of the reasons when you showed the results for the physics-informed model with only 20 experiments. Like one of them had beat the 1800 grid search experiments. The other two were still, they had not found a very good design yet. So I guess that's evidence that the approach can be sensitive to the starting. Which, of course, if you're only running it for 20 experiments out of a huge design space, it makes sense. But I'm wondering if there's been any research in like balancing, like surveying the design space with a very wide range and then like using that as a prior versus just choosing things at random.
Yeah, that's a really good question. I mean, when we started this work, we ended up doing a bunch of simulations, because once we had that 800 data set, which I'll note is freely available if anyone's interested, that's all hosted on my website, which is listed here in the bottom of the slide, /data. So if you go there /data, you can find all of our data sets, and so you can play with them yourselves. The thing that we played with this idea of like, well, can you switch between random sampling and maybe you could switch between exploration-based decision-making policies and exploitation ones, and those things probably could make a bit of a difference, right? They definitely could accelerate things a bit further. I think what we were at this point most excited about is sort of the differences between sort of random exploration or grid-based exploration and using an algorithmic decision policy. So I think there's definitely lots of sort of lingering advantage to be gained. I think the one thing I would caution against a bit is that one thing we've definitely learned from this is that the way you represent space and the kind of policy you should use is quite dependent on the type of space and its exact characteristics. And so I would just caution against sort of trying to draw conclusions that are too broad, right? In anything like this, right? I know there's a rule in the literature called the 4D rule, which is if you have a d-dimensional space, you should do 4D experiments randomly to find it. And I think that that's better than not having a rule, right? but it's certainly not going to adequately perform in any in all spaces. So in our case, we did the one rule. We only did one random experiment, and we probably could have perhaps done better if we done more. But that was certainly not the whole point of the work.
Right. As always the case in any engineering problem, the answer is always it depends. You can't apply one rule everywhere. And then so for the physics informed experiments with the FEA simulations, so was the approach to have the model propose a design, run the FEA simulation to use that as further input to the model, and then print the part every time unless it was excluded by having the predicted maximum resilience? Or did you kind of first do a campaign only in FEA, so you didn't actually have to run any experiments, and then take the best design from that and print, and then kind of repeat that process, so you're relying more heavily on the simulation so you can really cut down the number of experiments?
Yeah, so that's a great question. So and I didn't go into this in enough detail, so yeah, apologies. But in those campaigns, our original idea was, okay, so why don't we do this kind of cost analysis thing where we say, okay, here's the design we want to study. I'm going to have the bear choose whether to do a simulation or do an experiment, right? And what we kind of ran into with that is that the experiments are always going to be substantially slower than simulations. Simulations, well, most took anywhere between 5 and 30 minutes, something like this, individually, and the experiments took at least sort of 30 minutes to an hour, that kind of so they're always going to be quicker, but or the experiments are always slower. But then furthermore, there's not really a reason, since you can only do one thing at a time using each system, there's not really a reason to do both. And so we didn't answer the question of kind of resource allocation with this. Instead, what we did is we basically studied the whole space with simulation. We just did a complete study of the space, and then we used that as the prior knowledge. We actually didn't do any active learning in simulation at all. We started with a simulation database, which again is if you're interested, is available on that cablab.org/data. We started out with that database, and then we just went and we just took that as input, one way or another, into the Bear campaigns, and then used that to choose experiments. So there was no active learning as part of the simulation. There's actually been some really great work looking at active learning and simulation works, as you can imagine, that's much easier to implement, right? Because it's just, you can do that all using whatever one piece of code, whether it's MATLAB or Python or R or whatever. So, there's actually been some great work there. And so we thought the most impactful thing was to address the question of how can that prior knowledge be imported into an AE campaign, and how could it most be effectively used?
Very cool. Well, we are coming up on the top of the hour, and I'm not seeing any other questions posted in the chat. So I think I'll take the opportunity to thank you again very much for your time and for sharing your very cool research project.
Thank you very much.
Yeah, so I think this live session will be posted as a recording on YouTube so that it can be shared with anyone else who's interested, and for anyone who would like to refer back to the research. So yeah, thanks again.
Thank you, Ryan. Thank you, Aggregate Intellect. Been a pleasure. Follow us on Twitter.
Yes.
All right.